Hello, and welcome to this course on complex analysis. So, what is the goal of this course? The goal is to present sort of a standard one-semester graduate course on complex analysis. So the sort of course that most graduate students in pure and applied mathematics would see when coming into graduate school in the first year, generally. So the course is going to follow this book, Cultivating Complex Analysis, which is available freely online. You can buy a paperback copy if you want. I don't know if you can see it in the small window over there, but you don't have to. It's you can follow the PDF online, and the idea is that you should be following the book and and going through the exercises in the book. I'm going to mention some exercises explicitly, and not mention others. But you try. The more you try, the better, right? All right. The slides. So in case you're maybe interested in presenting this or maybe learning from the slides, those are also available. And the book itself is available the LaTeX source of it is available. And I've seen actually students use it. When they're typing up homework, they go in and just cut and paste the problems. So yeah, that's useful as well. So that's available in LaTeX. These slides are available in LaTeX as well. There may be a little bit more, messy LaTeX. More it's just making sure that it works out, but maybe it's not the best style of writing LaTeX, right? But the book, I think, is should be reasonably nice LaTeX, and the license for both is a Creative Commons license. So you can modify it, you can make your own version of it as long as you follow the license, meaning you're supposed to keep the attribution and you're supposed to keep it under the same license and all that. So all right. Now the goal is to record a short lecture, maybe every week or two, or maybe more often, less often, just however it will come out, for some foreseeable future. So hopefully, until it's finished. But it's probably not going to be a really fast progressing unless I get bored and try to do more lectures. But hopefully eventually it will go through the entire course. Now, at first, what I'm going to do before publishing any of them is record a bunch of lectures. So it's going to start with a bunch of lectures already recorded, just so that it's not just this this intro lecture. All right. So what are the prerequisites for this sort of course? Well, the biggest prerequisite is just some basic undergraduate analysis, and really, we're going to assume metric spaces. So sometimes in these sort of courses, metric spaces are, not assumed, and one would go through metric spaces. So here we are assuming metric spaces. We're assuming the Riemann integral, knowing how to interchange limits with the Riemann integral, and then with sums and all that. Generally, if you have uniform limits, right? Taking derivative under the integral. Just the simplest versions of these will actually be enough. Fubini, swapping the order of two integrals, right? So we're assuming all of that. We're also assuming the understanding the derivative in several variables. So namely, for functions from R2 to R2. So that basically the derivative, a differential function, right, of R2 to R2 is one where you can approximate the function locally by a linear operator from R2 to R2, right, meaning a matrix, a 2x2 matrix, right. Now, we're also assuming linear algebra in general, basic linear algebra. You don't have to have, very, very high-level linear algebra. Just basic linear algebra is going to be good enough, and some sort of basic abstract algebra. It's going to be good to know what a group is, what a field is, and so on. Right, but not, nothing too crazy, nothing too fancy. And overall, just experience with proofs, right? I mean, all of these, we're talking sort of undergraduate level classes are good enough, and you don't, not even everything in those classes is necessary. Just the very basics, really. But experience with proofs, you should sort of see all of that. Probably the analysis part, metric spaces, Riemann integral, all that, that's the stuff that we'll be using sort of, most, right? I mean, this linear algebra and abstract algebra, you need just a little bit. But we are going to go sort of quickly through some of these proofs, so we're not going to go into, extreme detail. So. All right, so what is the outline? So the outline of the course is to go through basically, so the book, let me pull myself out of the way. The book has, some sections and chapters are starred, and I'm not going to go through the starred ones, those are optional. So we're going to go through the non-starred parts of this. So, you're still welcome to read the starred bits, and they're nice, and, there's a reason why I put them in there, right? But we're not going to cover them in these lectures, right? So it's, so with chapter 1, we're going to cover basically the basic geometry of the complex plane, topology, one thing limits, the structure, there's a field and all that, right? All the basics, the Riemann sphere, the linear fractional transformations. I mean, a lot of this stuff, I'm assuming that you've maybe seen a little bit, maybe not as much. And I just noticed there's a misspelling of the Riemann sphere, so that's terrible. So the Riemann sphere, not the Riemann sphere, the Riemann sphere. So I'm assuming mostly this part that you've seen before, seen complex numbers somewhere in the abstract algebra course, in the undergraduate analysis course, stuff like that. So a lot of it is covering a little bit more quickly, and leaving stuff to exercises a lot. So that's sort of the basic basic setup for complex numbers. Next, we actually get into the sort of the meat of this course, which is the holomorphic and analytic functions. And we're going to see later, in a later chapter, that those are actually the same, right? So holomorphic functions are ones where you have the complex derivative, or another way of looking at it is there are functions that satisfy a certain partial differential equation or system of equations, depending on how you look at it. On the other hand, analytic functions are ones that have power series, right? That converge to power series, right? So those are analytic functions. Going to look at the exponential as an analytic function. We're actually going to define the exponential all the way out here. But this is probably the the good definition of the exponential, and maybe the fundamental term. It's not called the fundamental term, but one of the fundamental terms for analytic functions, the identity theorem, right? That if you know the function on a large enough set, you know it everywhere. So that's chapter 2. So just sort of these basics for holomorphic functions and power series and all that. Next, we get into into this Cauchy theory, really looking at line integrals in the plane and basic versions of Cauchy's theorem. So there's a whole bunch of different Cauchy's theorems. Generally, some sort of a line integral is 0. One way to think about it is that some sort of a line integral is path independent, and that gives us that surprisingly gives us quite a bit, right? We're actually going to get we're going to get from this a formula for holomorphic function in terms of values on the boundary, which should really be surprising. And once we have this formula, then we're actually gonna, then we can actually prove that holomorphic analytic functions are the same. Then we can go through some of the basic results that follow from all this. We're gonna get the maximum principle that holomorphic functions, the modules of holomorphic functions cannot achieve a maximum in the interior. We're going to get estimates on the size of the derivatives in terms of how far the function is still holomorphic. We get Liouville's theorem, which tells us that functions defined in the entire complex plane, if they're holomorphic and are bounded, there's actually just constants, and that immediately gives us fundamental theorem of algebra. Seems like it's a theorem of algebra, but it's really a theorem of complex analysis. We have, we're going to look at, convergence of sequences of holomorphic functions. Whenever you look at a set of functions, you want to know what, how do they converge, right? What's the right topology on the set of these functions? We're going to look at Schwarz lemma. Which again is some sort of estimate of the function depending on how far it is holomorphic, and it has lots of really neat consequences, and one of the basic consequences of all this is look at automorphisms of the disk. So really, those are really just all consequences of the maximum principle, really. So automorphisms of the disk, we're going to see that those are actually just these nice linear fractional transformation. And so these, this is basically looking at hyperbolic geometry. So in a very basic way. All right. Now, then we get to defining the logarithm, so the inverse of the exponential. The exponential in complex analysis is not invertible. It's not one-to-one. So this is an infinitely valued function, but it's actually very useful. And it's very useful that it is not a function, that it has infinitely many values is a key thing. And you can define it by continuing along path, right? The path, the things that you would integrate. That gives us these sort of winding numbers. How many times do I go around a point? And then we're gonna get, finally the actual version of Cauchy's theorem in terms of homology. How you're winding around certain points. Then we can define what simply connected domains are, domains without holes. We're going to look at Laurent series. which are there's a series around an isolated singularity. Then we get to counting these zeros and singularities. It's really sort of has to do with this logarithm. Basically, you want to maybe know how many zeros, how many solutions does a certain equation that happens to be holomorphic have inside of some loop or something. You can do that. You can do that by computing an integral. So you can count zeros and singularities. You can classify all of these, right? You can compute integrals based on basically looking at singularities, right? This is actually a very powerful theorem. It's sort of maybe hidden over here, but if you have an applied course, they would probably, this would be the sort of the key term to get to is the residue term, like a basic applied complex analysis course, like an undergraduate complex analysis course that is not necessarily proof-based, but maybe geared towards engineers. They want to get to the residue term so that they can use it to compute integrals. We get to the argument principle, Rouchet. Those are really about counting these zeros. You do Horvitz, that's really what happens to zeros when you're taking limits of functions. Open mapping theorem, which is sort of a more complicated version of the maximum principle in some sense, saying that holomorphic functions are open mappings. We also get that inverses are automatically holomorphic. You don't need to apply the inverse function theorem, or you could think of it as an inverse function theorem for holomorphic functions. It doesn't really require the derivative to be non-zero. You sort of get it automatically if you have a one-to-one function. All right. Now then we get to Montel and Riemann. So Montel and Arzelà-Scully is not really a term about holomorphic functions. It's about continuous functions, but that's the way that we prove Montel. And the idea is that you want some theorem, sort of like Bolzano-Weierstrass. That says, if you have a sequence of functions, if they're bounded in some way, then maybe you can take a convergent subsequence. It's not necessarily true for functions, but for holomorphic functions, it is actually true, strangely. Looking at these limits, we also get the Riemann mapping theorem. And the way that or what this says is that every simply connected domain in the complex plane, except for the complex plane itself, is biholomorphic, so equivalent as far as holomorphic functions are concerned to the disk, right? One way of thinking about holomorphic functions and what they do, especially biholomorphic functions. So holomorphic functions was a holomorphic inverse, which, as we said, just one-to-one holomorphic functions, is that they preserve angles. So that was actually a really neat thing that every domain in just R2 can be mapped to the disk with a map that preserves angles and orientation, which is actually kind of a really interesting result, right? So that's Riemann mapping theorem. And a lot of times that would be sort of, maybe end of the first semester, complex analysis, maybe, go more into harmonic functions. So harmonic functions, the way they come up here is that they're the real and imaginary parts of holomorphic functions, or so-called harmonic functions. Again, they're functions that satisfy certain a partial differential equation, the Laplace equation, the Laplacian of a function is 0. In this case, it's a second order PDE. So, sort of basic properties, and solve the Dirichlet problem in a disk. If you have boundary values that you can solve for a harmonic function in the disk. Harmonic functions are, for example, steady state heat. So if you have heat applied on the boundary of a domain, you want to figure out what's the, after a very long time, what's the heat inside at any point? Well, that's a harmonic function. That's also going to be, the solution to that is via the Poisson kernel, which is sort of like the Cauchy integral formula. And actually, this is, harmonic functions exist in all sorts of dimensions, but it's in dimension 2 that they have this really neat connection with complex analysis, with holomorphic functions, that they are the real parts of holomorphic functions. So a lot of times the harmonic, harmonic functions in, it's a different thing to study harmonic functions in R2 and in Rn. And so it's going to be really about harmonic functions in R2, right? Which are the same thing as harmonic functions on C. To get the mean value property, harmonic functions are exactly the things that are their averages, of their values in a circle. We have Harnack's inequality in principle. It's sort of like, sort of like Schwartz. Basically, getting some inequalities based on how far away you are still harmonic, and then we get to some maybe extending these past some singularities, remove the singularities and extending past boundaries. There's a reflection lemma, which actually also works for a holomorphic function that's going to come a little later in the book. Then there's a chapter on Weierstrass factorization. Basically, the basic idea is that you have a function. You want to maybe factor out the zeros, right? Well, what if it has infinitely many zeros? So can you factor it out? Yeah, you can actually. To figure out what infinite products are, it's like infinite sums. But it's maybe a little bit more complicated to take limits of infinite products, but not that much more complicated. And then factorizing, basically taking out the just like factoring a polynomial into linear terms, right? But now factoring functions that have infinitely many zeros. So that's Weierstrass. Then we have rational approximation. So that's really referring to Runge's theorem. You could, when can you approximate? Maybe by a polynomial, maybe by a rational function with poles somewhere, so with singularities somewhere. Polynomial doesn't have any singularities. So you want to approximate holomorphic functions by these guys. To a thing called polynomial hull that's really connected to simple connectedness. As long as things have no holes, you can approximate by polynomials. You can also get to Mittag-Leffler, which is which really gives us a way of constructing functions by which have certain specific singularities, and to do that, to make that work, we use actually it's an application of Runge's theorem of approximation by rational functions, where you have some control over where the singularities are. And then the last chapter is analytic continuation. So there's sort of two things here really. First, Schwartz reflection principle. That's the same reflection principle that I was talking about here, right? So that's saying that you can sometimes reflect across a boundary, right? So if you have the function that's holomorphic all the way up to the boundary, it's let's suppose that's the boundary is the real line, maybe all the way up to the real line, and it's real on the real line. Then you can actually extend it a bit past. You can sort of reflect the function past. You can also sometimes just continue along path, which is what how we do the maybe define the logarithm, and we'll really look at when does that work to define actual functions, right? So it's looking at monodromy theorem. All right, so that's basically the course. Now, a couple more notes before we leave it. So one of the things in this course and in the book is that I try to make connections to what you've seen before, rather than necessarily reinventing the wheel. So it's not completely self-contained on purpose. It's supposed to sort of give you connections to what you've seen, right? I mean, we've done all this sort of differentiability, or you've done all this differentiability of functions, all this basic analysis. And sometimes when you read a complex analysis book, it seems like it's not using any of that. Like, why did we figure all that out, and what's the connection to this? And it's really, it's using it's the same thing. We're not doing anything really new. We're just adding to it, right? So that's one point of view here, that we don't want to sort of on purpose. We're not making it self-contained. We want to have these connections to the stuff that you've seen before. So, for example, when I talk about the derivative, some people call it just the derivative. I always call it the complex derivative if it's just holomorphic derivative. And derivative, I really mean the real derivative, right? The standard derivative that you've seen in your undergraduate analysis class. So, so that you don't get confused between the two, because they are not, kind of the same thing, but not kind of the same thing. So, just saying something is differentiable is complex differentiable, is real differentiable. So in this class, it's always going to be real differentiable unless we say it's complex differentiable or holomorphic. Right. So that's I just said that. Now another thing, the last thing I want to mention is that maybe not completely doing this, but to a certain degree, I try to take the point of view of the z bar instead of x and y. Now, z and z bar, z and z conjugate, hopefully you sort of know what that is, whereas x and y are the real and imaginary parts. So the obvious way to sort of look at c is really to look at this thing, but the real and imaginary part, and think of it as R2, but it's almost it's almost better to think of in terms of z and its conjugate as your coordinates, right, on C, which is not quite right, because they're not independent variables. But a lot of times you can actually act as if they were independent variables. So we're going to do a little bit of that, but we don't want to sort of maybe overdo it with that. This appears in a lot of the exercises, for example. All right, so that's the course. So hopefully you'll if you stuck around this far into the video, maybe you'll watch some of the other lectures. All right.